Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Central University of Haryana. Today we are going to discuss about a module coupling of angular momenta selection rules under the paper Quantum Mechanics 1. The main points that we are going to be covering in this module are: first, vector addition of the two independent angular momenta. Then we shall discuss about the rules for the allowed values of J of the total angular momentum obtained by the coupling of two angular momenta with values J1 and J2 and the possible values that the magnetic quantum number M can have in terms of M1 and M2, where M1 corresponds to the magnetic quantum number values for the total angular momentum J1 and M2 corresponds to the magnetic quantum number values corresponding to the total angular momentum J2. After that, we would discuss a specific example of the allowed values of J for the given values of the two angular momenta and the corresponding magnetic quantum number values, that is M values. And finally, we will discuss an example of constructing the states for coupling of the uncoupled states using the technique of lowering angular momentum operator. Having introduced the coupled and uncoupled representations and defined the Clebsch-Gordan coefficients in the preceding module, we shall here discuss the selection rules for the non-zero values of the Clebsch-Gordan coefficients for the J1, J2, M1 and M2 states, where J1 and J2 are the total angular momentum states corresponding to particles 1 and 2, and M1 and M2 are the corresponding magnetic quantum number values associated with J1 and J2 respectively. We shall find that for addition of two angular momenta of values J1 and J2, firstly, the allowed values of the total angular momenta J, which can run from or take values from J equal to J1 plus J2 to modulus of J1 minus J2, where J varies by integer or as integral values, and for each value of J, there are two J plus 1 values of the magnetic quantum number M, where M takes the values from J, J minus 1, J minus 2, so on to minus J plus 2, minus J plus 1 and minus J. And secondly, M, the total magnetic quantum number, is equal to M1 plus M2, where M1 is the magnetic quantum number corresponding to the total angular momentum J1 and M2 is the magnetic quantum number corresponding to the total angular momentum J2. Allowed values of the total angular momentum J. To find out the allowed values of the total angular momentum J for given values of the total angular momentum J1 associated with particle 1 and the total angular momentum J2 associated with particle 2, we use the relation the z component of the total angular momentum operator Jz is equal to the sum of the z components of the total angular momentum operator of the first particle J1z and the total angular momentum operator of the second particle J2z, and operate these operators on the state Jm, and when we do this, what we get is The z component of the total angular momentum operator Jz acting on the eigenstate Jm is equal to operator J1z plus operator J2z acting on the eigenstate Jm, where operator J1z is the z component of the orbital angular momentum operator and operator J2z is the z component of the orbital angular momentum operator of the second particle. And this turns out to be equal to m times h cross times summation over m1, m2, the Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j acting on the state vector j1, j2, m1, m2, and this turns out to be equal to summation over m1, m2, Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j times bracket open j1z operator plus j2z operator bracket close acting on the state vectors j1, j2, m1, m2, and this gives us the result within brackets m1 plus m2 times h cross times summation over m1, m2, Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j acting on the state vector or the eigenvector j1, j2, m1, m2. And if we work this out, we finally get the result summation over m1, m2 within brackets m minus m1 minus m2 times Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j acting on the state vector or the eigenvector j1, j2, m1, m2, and this turns out to be equal to 0 because m is equal to m1 plus m2. So m minus m1 minus m2 term inside the summation yields 0. Selection rules for allowed values of j and m. That means selection rules for the allowed values of total angular momentum j and the magnetic momentum vector m. Now, since the state vectors are linearly independent, therefore it follows that the Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j turns out to be equal to 0 if m is not equal to m1 plus m2, according to the relation that we have discussed earlier. And the Clebsch-Gordon coefficients C subscript m1, m2, m superscript j1, j2, j are not equal to 0 if m is equal to m1 plus m2. Now, since the maximum values of m1 and m2, that means the maximum values that m1 and m2 can take are j1 and j2 respectively, since m1 will take values from minus j1 to plus j1 including 0, that means 2 j1 plus 1 values, and similarly m2 will take values from minus j2 to plus j2 including 0, that means 2 j2 plus 1 values. Therefore, from the relation m is equal to m1 plus m2, using the maximum values that m1 and m2 can take, we get the maximum possible value of m as j1 plus j2. Now, for the case j equal to j1 plus j2 and where m takes its maximum possible value, m is also equal to j1 plus j2. In such cases, there will be only one case corresponding to M1 is equal to J1 and M2 is equal to J2. In the sum on the right hand side of the equations that we have discussed earlier. That means the equations that were involving the state vectors Jm, and from this we finally have state vector Jm can be written as state vector J1 plus J2. J1 plus J2 is equal to Clebsch-Gordon coefficients C subscript J1 J2 J1 plus J2 superscript J1 J2 J1 plus J2 times ket vector J1 J2 times ket vector J2 J2, that is equal to Clebsch-Gordon coefficient C subscript J1 J2 J1 plus J2 superscript J1 J2 J1 plus J2 times ket vector J1 J1 ket vector J2 J2, where for M we have used its maximum value, that is J1 plus J2, and for M1 we have used its maximum value J1, and for M2 we have used its maximum value, that is J2. Selection rules. Now, using the orthonormal properties of the states, we get bra vector J1 plus J2, J1 plus J2, ket vector J1 plus J2, J1 plus J2 is equal to 1 is equal to square of the modulus of the Clebsch-Gordon coefficients C subscript J1, J2, J1 plus J2 superscript J1, J2, J1 plus J2, where for both total J and total M we have used the maximum values for M, that is J1 plus J2, and for J we have used the values J1 plus J2. Similarly, in determining the Clebsch-Gordon coefficients also. Now, this equation gives the value of the Clebsch-Gordon coefficients as C subscript J1 J2 J1 plus J2 superscript J1 J2 J1 plus J2 is equal to exponential of iota times delta, where delta is real and it is chosen to be 0, giving the phase of the state J1 plus J2 J1 plus J2, so that the Clebsch-Gordon coefficient C subscript J1 J2 J1 plus J2 superscript J1 J2 J1 plus J2 turns out to be equal to 1. So with this choice of delta being taken as 0 and the Clebsch-Gordon coefficient turning out to be 1, we fix the phases of all the Clebsch-Gordon coefficients belonging to J equal to J1 plus J2. Now, considering the case of J equal to J1 plus J2, but M is equal to J1 plus J2 minus 1. That means that M is now no longer taking its maximum value, but is taking the value J1 plus J2 minus 1. And for this value of M, the possible values that M1 and M2 can take are either M1 is equal to J1 and M2 is equal to J2 minus 1, or M1 is equal to J1 minus 1 and M2 is equal to J2. Thus, the state Jm must be a linear combination of these two different values that M1 and M2 can take of the two linearly independent eigenstates J1, J2, or they must be a linear combination of two linearly independent eigenstates J1, J1, J2, J2 minus 1, which corresponds to M1 is equal to J1 and M2 is equal to J2 minus 1, and the eigenstates J1, J1 minus 1, eigenstate J2, J2, where which corresponds to M1 is equal to J1 minus 1 and M2 is equal to J2. Allowed values of J. Now notice here that there are two such linear combinations that are possible. One belonging to the state J is equal to J1 plus J2, and the other orthogonal combination is a member of the eigenstate for which the maximum value of M is J1 plus J2 minus 1. This latter set must be such that J is equal to J1 plus J2 minus 1. So proceeding in this way to the state J is equal to J1 plus J2, but with M having the value J1 plus J2 minus 2, there exist three linearly independent states corresponding to the values of J equal to J1 plus J2, second J equal to J1 plus J2 minus 1, and the third corresponding to the value of J equal to J1 plus J2 minus 2. Each time the magnetic quantum number M is reduced by unity, one of the coupled states which arises belongs to a J value reduced by unity, and in this state the magnetic quantum number M has its maximum value. Evaluating J max and J min, that is the maximum value of the total angular momentum eigenvalues and the minimum value of the total angular momentum eigenvalue. Now the lower limit of the eigenvalues associated with the total angular momentum J min is reached when the number of coupled states has matched with all the uncoupled states. So let us understand this through the following illustration. We know that summation over J min to J max of 2J plus 1 is equal to 2J1 plus 1 times 2J2 plus 1, where the maximum value of the eigenvalue associated with the total angular momentum J, that is J max, is equal to J1 plus J2, and the minimum value of the J eigenvalue, say alpha, can be determined by using the relation summation going from alpha, that is the minimum value of the eigenvalue J, to J max, which is the maximum value of the eigenvalue J, over J is equal to half times the commutation is equal to half times J max is equal to half times bracket open J max times J max plus 1 minus alpha times within brackets alpha minus 1 bracket close. We find that the square of the eigenvalues of J min, that is J min square, is equal to within brackets J1 minus J2 whole square, and this gives the value of the minimum eigenvalue for J, that is J min, equal to modulus of J1 minus J2. Thus, from the above discussion, we arrive at an important result, that is the addition of two angular momenta operators. If the total angular momentum operator J is equal to J1 operator plus J2 operator, then the eigenvalues of the operator J1 square are J1 times within brackets J1 plus 1, and the eigenvalues of the square of the J2 operator, that is J2 square, are J2 times within brackets J2 plus 1. Then the eigenvalues associated with the square of the total angular momentum operator J square are J times within brackets j plus 1. Triangular condition for j1, j2 and j. Now, as we discussed earlier, if the total angular momentum operator is defined by the relation operator j1 plus j2, where j1 have the eigenvalues j1 and the square of the j1 operator has eigenvalues j1 times j1 plus 1, while the eigenvalues of the square of the j2 operator, that is j2 square, are j2 times within brackets j2 plus 1, then the eigenvalues corresponding to the square of the total angular momentum operator j square are j times j plus 1 within brackets, where j can take values from j1 plus j2, comma j1 plus j2 minus 1 and so on to modulus of j1 minus j2. Here the three angular momenta, that is j1, j2 and j, satisfy the triangular condition modulus of j1 minus j2 is less than equal to j is less than equal to j1 plus j2. That means the total angular momentum j lies between modulus of j1 minus j2 and j1 plus j2. And for each value of j, there are two j plus 1 values of m, given by m is equal to minus j plus 1, minus j plus 2 and so on to j minus 2, j minus 1 and j. These relations serve the basis of the theory of addition of angular momenta. Examples of constructing states. Now, in order to understand how we can construct coupled states by considering addition of angular momenta, let us take an example where the total angular momentum of the first particle j1 is given by 1 and the total angular momentum of the second particle j2 is also given as equal to 1. To get the total angular momentum of the combined state, j is equal to j1 plus j2, and the values can range from j1 plus j2 to modulus of j1 minus j2. So we get three different values of j, which are 2 corresponding to j1 plus j2, 1 and 0 corresponding to modulus of j1 minus j2, where 1 corresponds to the value j1 plus j2 minus 1. Now, corresponding to the value of j equal to 2, the possible values that m can take or the projections that this angular momentum vector can take are m is equal to 2, 1, 0, minus 1 and minus 2. That means m can take 5 values, which can also be obtained from the relation 2j plus 1. So if j is equal to 2, twice of 2 gives us 4 plus 1 is 5. So m can take 5 different values, which have been given over here as 2, 1, 0, minus 1 and minus 2. In the subspace of j equal to 2, the ket vector j equal to 2, m equal to 2 can be written as ket vector 2, 2 is equal to j1 equal to 1, j2 equal to 1, m1 equal to 1, m2 equal to 1, and this is equivalent to ket vector 1, 1, 1, 1. To get the vector state j equal to 2, m equal to 1, we apply the lowering operator j minus on the left to get the following relation. So operator j minus acting on the state 2, 2 is equal to h cross times under root of bracket open j plus m whole times within brackets j minus m plus 1 bracket close acting on the state 2 1 where h cross times under root bracket open within brackets j plus m times within brackets j minus m plus 1 times bracket close is the eigenvalue corresponding to the lowering operator j minus acting on the state 2 2, and this for the values of j equal to 2 and m equal to 1 yields the result 2h cross acting on the state 2 1, where 2h cross is the corresponding eigenvalue of the eigenstate or the eigenvector 2 1. Now the lowering operator j1 minus will operate on particle 1 and the lowering operator j2 minus will operate on particle 2. So before doing this, if we look at the above relation, the state 2 1 in terms of the state 2 2 can be written as state 2 1 is equal to 1 upon 2 h cross times the lowering operator j minus acting on the state vector 2 2, and this is equal to 1 upon 2 h cross times bracket open j1 minus plus j2 minus bracket close operators acting on the state 1 1 1 1, where the lowering operator j1 minus is the lowering operator of particle 1 and the lowering operator j2 minus is the lowering operator of particle 2. So working this out further, the state vector 2 1 is equal to 1 upon 2 h cross whole times lowering operator j minus acting on the state 2 2 or the state vector 2 2 gives 1 upon 2 h cross whole times bracket open lowering operator j1 minus plus lowering operator j2 minus bracket close acting on the state 1 1 1 1, and this turns out to be equal to 1 upon 2 h cross bracket open h cross times under root of within brackets j1 plus m1 times j1 minus m1 plus 1 bracket close acting on state vector 1 1 0 1 plus h cross times under root of within brackets j2 plus m2 times j2 minus m2 plus 1 acting on the state vector 1 1 1 0, the whole bracket close. So now when we perform these operations, the final result that we get is state vector 2 1 is equal to 1 upon under root 2 whole times bracket open state vector 1 1 0 1 plus state vector 1 1 1 0 bracket close. So here we can use the operator j minus, that is the lowering operator on the state defined by j is equal to 2 m is equal to 1 to get the state or the ket vector j equal to 2 m equal to 0 in a similar manner as we obtained the ket vector or the state j equal to 2 m equal to 1. So ket vector or the state 2 0 turns out to be using the lowering operator j minus on the state or the ket vector 2 1 as 1 upon under root 6 whole times within bracket state vector or ket vector 1 1 1 minus 1 plus twice state vector or ket vector 1 1 0 0 plus state vector or ket vector 1 1 minus 1 1 bracket closed. In a similar manner, we can further continue operating the lowering operator J minus on the state j equal to 2, m equal to 0 to give the states j equal to 2, m equal to minus 1 and the state or the vector j equal to 2, m equal to minus 2. So for obtaining the ket vector or the state vector 2 minus 1, we operate the lowering operator j minus on the state to 0, and the state vector 2 minus 1 turns out to be equal to 1 upon root 2 times whole times bracket open state vector 1 1 0 minus 1 plus state vector 1 1 minus 1 0 bracket closed, and the state vector 2 minus 2 is simply the state vector 1 1 minus 1 minus 1, where the four components of the state vectors correspond to J1, J2, M1 and M2 respectively in all the above equations that we have used. Now, if we proceed to calculate the state vector J equal to 1, M equal to 1, we note that this vector must be a linear combination of two basis kets or the two basis vectors 1 1 1 0 and 1 1 0 1, where these four values of the two basis vectors or ket vectors are j1, j2, m1 and m2, and the linear combination in this must be only for those values for which m is equal to 1. So let us set the ket vector or the state vector 1 1 equal to alpha times vector 1 1 1 0 plus beta times ket vector 1 1 0 1, with the condition that modulus of alpha square with the condition that square of the modulus of alpha plus square of the modulus of beta should be equal to 1. Constructing states. Now, since the states must be orthogonal to the state or ket vector to 1, it is necessary that alpha plus beta should go to 0. Now, if we choose alpha and beta to be real, and by convention, if we make alpha as positive, we get the state vector or the ket vector 1 1 equal to 1 upon root 2 whole times bracket open state vector or ket vector 1 1 1 0 minus state vector ket vector 1 1 0 1 bracket closed. Now applying the operator j minus, that is the lowering operator on this state to get the ket vector or the state vector 1 0, and applying the lowering operator on the state vector or ket vector 1 0 to further get the state vector or ket vector 1 minus 1, we obtain state vector ket vector 1 0 is equal to 1 upon under root whole times bracket open state vector or ket vector 1 1 1 minus 1 minus state vector or ket vector 1 1 minus 1 1 bracket closed, and for the state vector ket vector 1 minus 1 we obtain the result 1 upon under root 2 whole times bracket open 1 state vector ket vector 1 1 0 minus 1 minus state vector or ket vector 1 1 minus 1 0. Now, in order to calculate the state vector ket vector corresponding to j equal to 0, m equal to 0, we note that this is a linear combination of the three basic kets of m equal to 0, that is the state vector ket vector 0 0 is equal to alpha times state vector or ket vector 1 1 1 minus 1 plus beta times the state vector or ket vector 1 1 0 0 plus gamma times the state vector or ket vector 1 1 minus 1 1, with the condition that square of the modulus of alpha plus square of the modulus of beta plus square of the modulus of gamma is equal to 1. We note that this state is orthogonal to the ket vector or the state vector 2 0, as well as the ket vector or the state vector 1 0. Construction of the state Jm basis for J1 equal to J2 equal to 1. So now when we put the conditions that square of the modulus of alpha plus square of the modulus of beta plus square of the modulus of gamma is equal to 1, and we note that the state 0 0 is orthogonal to the state 2 0 and 1 0. So with these conditions we get alpha plus twice beta plus gamma is equal to 0, and alpha minus gamma is equal to 0. So the relation alpha minus gamma equals to 0 yields alpha is equal to gamma, and substituting this relation in the above relation, that is alpha plus 2 beta plus gamma is equal to 0, the final relation for alpha, beta and gamma turn out to be alpha is equal to minus beta is equal to gamma. And choosing these values of alpha, beta and gamma and taking them to be real and taking the value of alpha to be positive, we get the state vector or ket vector 0 0 is equal to 1 upon root 3 whole times bracket open state vector or ket vector 1 1 1 minus 1 minus state vector or ket vector 1 1 0 0 plus state vector or ket vector 1 1 minus 1 1 bracket closed. With this, we complete the construction of the basis of the state vector or ket vector Jm for the case J1 is equal to J2 is equal to 1. Now, after having gone through this module, let us understand what all we have learned, and let us also summarize what all we have absorbed. So, we started this module with understanding the vector addition of two independent angular momenta. Then we discussed the rules for the allowed values of the total angular momentum J and obtained the values of the total angular momentum J by the coupling of the two angular momenta with values J1 and J2, and the possible values of the magnetic quantum number m that it can have in terms of m1 and m2. So here we saw that J was taken as J1 plus J2, where J1 had a magnetic quantum number m1 associated with it, while J2 had a magnetic quantum number m2 associated with it, such that m1 could take two J1 plus 1 values ranging from J1, J1 minus 1 and so on to minus J1 plus 1 and minus J1. Similarly, the magnetic quantum number m2 associated with the total angular momentum values J2 could take two J2 plus 1 values ranging from J2, J2 minus 1 to minus J2 plus 1 and then minus J2. After that, we, through a specific example of the allowed values of the total angular momentum J for the given values of the two angular momenta and the corresponding magnetic quantum number values m, try to understand this entire process and the formalism. Then we also discussed another example which we used for constructing the states for coupling of the uncoupled states using the technique of the lowering angular momentum operator. Thank you.